Extended Range Guided Munition program was Draper's first pioneering demonstration of gun-fired competent munitions. The program, the initial part of the program, was more or less developed by some combination of John Elwell and Jim Sittimer.
The Navy want to have shells that are shot from a gun that will go to a range of 30 miles. Why? Because the Navy had a new strategy that called from the sea. They felt that their major role in the new battleground would be to support the Marines, that they are landing on a shore and they need fire support. But they didn't want the ships to go closer than 20 miles. What they suggested is to have extended range, to put a rocket motor on that shell and shoot it from a gun, and then when it starts going up, fire the rocket, and that will give it the range. The problem is if you go above 20, 30 miles, if you don't have a guidance system, you get an error of about 1 kilometer. So that's not a good fire support. The Navy was still looking at a solution, and Elwell said, wait a minute. Those MEMS instrument with the GPS will be able to do the job. And you actually don't need more than what we call an automotive quality gyros, like 1,000 degrees per hour. And we could build them at that time.
And because MEMS, inertial MEMS, were very small and had very low mass, they were ideal for high G applications.
The program was very exciting for us. It had many challenges. We had never, nor had anyone else ever, designed, developed, and done proof of concept testing of a high G survivable guidance system that would meet the timelines with regard to GPS acquisition, tracking, and guidance that we were going to do on this program.
And when I talk about the high G environment for the gun launch application, we're talking tens of thousands of Gs over millisecond durations.
You know, I'm 200 pounds in a 1G field. If I was in a 10,000 G field, I would weigh 200 pounds 10 times 10,000 Gs. That's what I would feel like. So when an accelerating body really has to deal with a lot of forces imparted by those accelerations, and it causes a lot of stresses.
Our first DARPA MEMS contract, called the High G High Dynamic Range Accelerometer Program. That program developed an array of accelerometers that was designed to survive up to 100,000 Gs and then measure down to the milli-G. So for that project, we started our initial testing at Draper using a 100,000 G centrifuge that we acquired from Department of Energy, and we installed underneath our parking garage in a steel reinforced room.
Extreme environment provided by a 10,000 G, and we've gone up to 50,000 Gs. In some of our early work, we did 120,000 Gs. Really, it comes down to, how do you make sure that your system is mechanically configured in such a way that the forces imparted by those high launch accelerators do not exceed the stress limits of your components.
So the first thing we did was tested it, and then we put it through the environment, and then we tested it again to make sure it worked. That was easy. The harder part was to make sure it operated when it was under the high G environment. So for that, we had to actually put it in projectiles and then extract the information as the projectile was shot. The soft catch facility was basically a long barn where they towed a field howitzer into one end, And at the other end, they filled a large room, probably a 10 by 20 room, with bales of hay. And they loaded our test projectile in the howitzer and fired it into the bales of hay. And then we quickly dug through the bales of hay with pitchforks, trying to find the projectile before the batteries ran out so we could recover the data. The first time we actually lost the projectile, we couldn't find it, and when we finally found the projectile an hour later, the batteries were dead and we lost the data.
So again, the first check mark we needed to show the Navy in particular was that the mechanical components had the survivability. And then once we accomplished that, then we were awarded the ERGM program. The MEMS inertial system was able to sense rates and accelerations, but not accurately enough to enable a fully inertial navigated solution to hit the 10-meter sorts of performance requirements that we had on the program. So the idea was more or less to integrate the inertial and GPS together so that the inertial could provide the high-frequency measurements required to stabilize the projectile, while the GPS provided the overall accuracy that enabled the projectile to guide to the target.
What we really needed in order to do this was technology that was not yet available, direct Y acquisition GPS receivers. What we had in the early to mid-90s were state-of-the-art receivers that first acquired the commercial CA code, and once it was acquired, transitioned into Y code track. The problem with that kind of technology was that it took minutes in order to go through CA code track and then hand off to Y code track. And the entire mission length for these demonstration programs was on the order of a couple of minutes. What we were able to do through a series of innovations was to utilize that existing then state-of-the-art technology with knowledge of what the trajectory was going to be, rough knowledge of the launch coordinates, and so on, to effect an approximation to a direct Y acquisition system. And that gave us the ability to acquire GPS and track it within 20 seconds of the round being launched out of the gun. Problem that we had observed in laboratory testing and other activities that the MEMS gyros would go into a feature where they stuck. And that meant that they would not turn on and they wouldn't measure inertial rate. And so we had built up the system, we had integrated the system into the projectile, and the only recourse we had if we had a sticking gyro in the field was to actually hit the munition with a hammer.
They were telling me one of the gyros is stuck, it's not responding. So I had all of the documentation at home with me in the event that they called and needed some support. And I'm looking at the documentation, and I believe I was talking to Tom Thorvaldsen, and I said, do you have something heavy like a hammer or a wrench? And I want you to go to this part of the projectile and I want you to hit it. And I think it was John Dowdle in the background. He wants us to do what?
So the test engineer, Brad Goosens, I believe, actually brought a sledgehammer to the flight test with him.
And I was like, just trust me, do this, get something heavy and go to this part of the projectile. There's no warhead in this projectile or anything like that. It's a flight projectile, so nothing was going to blow up. But what I was trying to do was impart enough mechanical shock into the gyro that it would shake free whatever was binding it. And basically they did that, it worked, and we had a successful test flight.
People looked at what we actually got out of the MEMS inertial sensors, and it was surprisingly good. It gave a lot of confidence. So there are a number of things that were true successes, absolute successes on this. We survived a high G environment of 6,000 Gs. We acquired GPS in about 20 seconds or some number thereabouts. While the system was 126 cubic inches in volume, which think about a big coffee can, and had to be put into something that was on the order of 8 cubic inches, so we had a lot of technical challenges to go. We'd put to bed a whole range of technical risks.
And now what we had to do was to take this 130 cubic inch system and put it into the fuse of the shell.
On ERGM demo, we did guidance and navigation. Control was already built into the round. We had to also add control into this fuse replacement system, and we had to shrink the total volume to the original goal, I believe, was 6 cubic inches. What we actually did was 8 cubic inches.
Again, making the leap from ERGM to CMATD really required, in all honesty, a different technology. And I remember the first quarter of that program, we really struggled. We couldn't figure out how to meet the volume requirement.
There were a lot of challenges. The miniaturization of the technology was huge. We had to work with the GPS vendors, and principally it was Rockwell Collins, to develop a very small, high G survivable GPS receiver that was capable of direct Y-code acquisition.
I'll phrase it this way: the two advancements that really enabled the volume reduction from ERGM demo to CMATD was multi-chip modules and ASICs.
With the ERGM demo program, the guidance system was in the rear of the projectile, which is an inherently stable position to put this mass. With the competent munition program, the guidance, navigation, and control system was in the front.
Yeah, I think CMAT demonstrated survivability, demonstrated the ability to do direct PY code reacquisition, demonstrated the ability to do trajectory modification, come up with a full nav solution. So it was a very successful program.
I can tell you when we went to Yuma to shoot that shell, and that shell hit the target, it was really something. There's no satisfaction, better satisfaction than building something. It was relatively complicated, and see it working. It was great.
A technology developed that had real-world applicability, that was demonstrated and applied, and then transitioned to production for DoD use. You know, it really went about as well as we could have anticipated it going.